So, incidentally, so this is an experiment, the video. So we thought that this would be useful. Also, we also have a, so what it can be useful to you, and if you want to go back to your lecture and maybe look at it. And also we have an online class, and so far we have taught the online class, I don't know, 4 times or so. And there is no audio or video, just the slides. And apparently, I used to think that maybe students will have some serious problems without audio or video, but somehow they are able to figure out things, and so they don't seem to have, they complain a little bit that there's no, so here of course we are here and we discuss things, but in the online class it is not there, the slides are there. There's some supporting material there. And I think the slides are fairly, they don't have the detailed discussion in there, but the main ideas are all there. So somehow they managed to kind of figure out what it is about. But it would be good to have the video. So we are expecting, I forgot, I was going to check. You suggested a couple of rooms, right? Did you send an email with some suggestions?
No, sir, that's not me.
Oh, I see. Okay, maybe we can talk about that later. So would it be nice if there was some light coming up from here? And I thought maybe I'll get some light and plug it in somewhere here. But actually there's no way to plug it in. So anyway, So in the classic bar curve, the assumption is that failure rate goes this way. And in the beginning, we have some high failure rate, and this is known as the burn-in period, and is also known as the infant mortality. Now it is kind of probably in bad taste to refer to that as infant mortality, but it's in a way not a bad term, because if you look at statistically, then infants have a much higher mortality rate. And if you look at it, it's sort of part of nature's design to burn-in is part of the manufacturer's design, part of their scheme to remove the weaker units from being shipped out. So typically whenever any electronic things are manufactured, for example a computer, it will be burnt in, or components. And if it fails early, that means it was a weaker component and it is removed. So here at the beginning, the units failing are the weaker devices. So as the number of weaker devices decline, stronger devices survive. So the failure rate goes down. And then here is your, this is your wear out period. So at this time, basically the unit has aged, and because of age, the failure rate starts going up. And in between, this is called operating life. And during the operating life, it is assumed that the failure rate is relatively constant. Now if you think about it, so why does this flat area arises? And actually it is a combination of the two factors. So you always have the process by which weaker devices are being removed from the scene, and hence making the failure rate go down. And you always have this phenomena of wear out. So there is some wear out mechanism that's always going on, and is gradually increasing the failure rate. So for this period, they kind of balance out the two opposite, and hence the failure rate is constant. Now there are some people who say that, now let me mention the controversy. Some people say that this is actually, do you think this is reasonable? Bathtub curve? Is this what you would normally expect for most things? So people often accept it without challenging, but there are some papers, some authors have questioned it, and they say that, especially for semiconductor devices, the burn-in period keeps on going on and on and on. Basically, the wear-out period, the wear-out process is rather weak. So as a device gets older, it becomes more reliable.
Mm-hmm.
Does that make sense? Something that gets older is more reliable?
Why?
Do you think that makes sense?
No,
Why not?
because the older it gets, the more we go towards the wear out level, or like the wear out area, and the more if your device is wearing out, then the function of it's still functioning, but it's not performing in the same way at the time it was designed.
Yeah, that is true. So if you assume that there is a wear out period, and you are getting there, then with old age, then because of the wear out, the failure rate would increase. But what they have found, people have looked at some data, and somebody argued that, okay, look at the data for electronic devices. I don't see any evidence of a wear out period. So basically this burn-in phenomena, it continues. So weaker devices are getting reduced from the pool, and whatever remains are the stronger devices, and the process keeps going on and on. And remember, for electronic devices, after a certain number of years, you throw them away. So you don't really care what happens. So let's say if you have a PC, you probably don't care what happens to it after 10 years, right? Anyone if you have a 10-year-old PC? But I have one, but I'm hoping that it will become a collectible. So, so PC typically gets replaced in like 3, 4, 5, 6 years, depending on how much disposable money you have. So for a lot of times, so there are some people who have questioned the bathtub curve, and especially this part.
So I think this should be affected by the way we use the unit and also like the environment surrounding the unit. So can we just judge that, like assuming that the unit is isolated, like or they will all go through the same, usage and
Yeah, so so normally we assume that when a device is operating, the circumstances are same, so we are not doing something that will suddenly put a lot of stress on the device. So we are assuming that is not happening. But whatever, we are going to assume that the failure rate is constant. And remember, if you don't assume failure rate is constant, analysis is going to be a lot harder. So at least for to begin with, while we are trying to understand how we should calculate these things, that is a good assumption. And if you want to relax this restriction, you can do that. There are methods available that will allow you to consider the case when the failure rate is not constant. In fact, we will see that this, we have already seen that this gives rise to the exponential distribution for time to failure. And if that is not true, you can switch to Weber distribution, and variable distribution will can take into account any possible aging. So methods are available, although I will basically just briefly mention about them. Okay, so let us come back then to the case of the basic case when we have a single unit with permanent failures. So continuing that. Now remember, we are using the time failure rate. And failure rate as the unit of per unit time because it's a rate. And we are assuming constant failure rate. Now let me ask one more question about constant failure rate. Let us assume that the constant failure rate assumption is true. The MTTF of a device is 1 year. And so right now I calculate MTTF and I figure that its MTTF is 1 year. Now at the end of the 1 year, what should I expect? Should I expect it to suddenly stop, to stop working or continue working? Assuming that the failure rate is constant.
It's gonna stop.
So if the failure rate is constant, that means after 1 year, things are exactly the same as they are today, the 1 year ago, right?
Mhm.
So there is no aging. So there's nothing wrong. So nothing has happened. So there is no change in as far as probability, as long as the failure rate, as far as the failure rate is concerned. So 1 year from, if MTTF right now is 1 year, a year from now, if it is working, is MTTF is still 1 year. And that is because we are assuming there is no aging. So constant failure rate assumption means no aging. So that's something that you kind of have to think about. So here's the system. So here we have the failure rate. In general, failure rate could be a function of time, but here let us assume that it is constant, and the constant failure rate is lambda. And here is the good state, and here's the bad state. Let's call them 0 and 1. And then we can describe the change of the probability of being in state 0 by this. Since the rate of change of being here is equal to probability you're here multiplied by the probability that you will have this transition. And let us assume that P00 is equal to 1. Initially, you know that you are in this state. And then, now we need to solve this equation, this differential equation. And in fact, we had solved this, the same equation we had solved earlier. And we know that its solution is that is the solution. And hence, now this is another important expression that you should remember. And this is sometimes referred to as the exponential reliability